The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading interdisciplinary solutions to address significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. PAIR research areas include advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation, look into the factors and mechanisms influencing human health and wellness, and develop evidence-based solutions, and generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation, and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions, Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good morning, ladies and gentlemen. Welcome to this PAIR Distinguished Lecture Series. My name is Qingyan Chen. I am the Director of the PolyU Academy for Interdisciplinary Research, or PAIR. It's my great pleasure to introduce our speaker today, who is Professor Lidia MORAWSKA, who is from the University of Queensland Technology. So Professor MORAWSKA is a distinguished professor and also Australian Laureate Fellow at the University. Professor MORAWSKA is a well-known expert in air quality and health, particularly in the science of airborne particulate matter. She combines expertise in physics, engineering, environmental science, and public health to address some of the world's most pressing challenges. Her pioneering research has advanced our understanding of the pollution sources, the behavior of ultrafine particles, and the strategies to reduce air pollution and its health impact. Among her most significant scientific contribution is her leadership in the global effort to establish that the SARS virus is primarily airborne, which is super important for most of us because we still have a very fresh memory about her contribution. Let's say because during the COVID pandemic, Professor MORAWSKA brought together an international coalition of nearly 240 scientists from 34 countries to present the compelling evidence airborne transmission to public health authority worldwide. So I think Professor Lee and I are very lucky to be one of those scientists in the list. So that effort really helped to shape the international health guidance, leading to the greater emphasis on ventilation, air filtration, and other measures that help to protect millions of lives. So a long-standing advisor to the World Health Organization, Professor MORAWSKA has been recognized globally for her impact. She was named one of the Times Magazine's 100 most influential people in 2021 and has received numerous prestigious honors, including the Laureate UNESCO for Women in Science International Award in 2023 and Australian Prime Minister's Prize for Science in 2025. So without further ado, ladies and gentlemen, please join me in welcoming our distinguished speaker, Professor Lidia MORAWSKA.
Good morning, everyone. Ni hao. Many thanks, Professor Yang Chen, for inviting me to give this prestigious lecture. I really feel humbled and very grateful to be here. Thank you very much. But it also feels like almost coming home. Just looking even around this room, how many people we've worked and for how long together. So it is just really so nice to be here. Thinking about what to talk, there are lots of things we could have talked. But I chose this topic, the world of the particles we inhale and how to control it, because there is not just science, but it is what to do with this science, which is equally important. And there are different elements to these actions, dependently on which particles we talk about. So I'll be talking, well, first of all about airborne particles, why and what. I'm assuming that not all of you is that familiar with airborne particles. Then specifically ultrafine particles, infectious respiratory particles, microplastics in the air, and finally science versus regulatory oversight. But I'll first start with how did it start? My background is in nuclear physics. My first degree is in nuclear physics. And then during my PhD, I kind of branched into environmental radioactivity. And this was radon and radon progeny in the air. So it's a complex process what happens. And one of my first paper was on influence of sealant on radon emanation from building materials. But there are many issues into radon exposure, which is still the most significant radiation exposure. But this is radon. So what attracted me to study particles in the air? By that stage, I was in Toronto. And in Toronto, I was doing investigations on the attachments of radon progeny to airborne particles, because dependently if they are attached or unattached, their fate in the air differs. And I was lucky there to have access to these instruments, which is called differential mobility particle sizer. At the time, one of the few in the world which measures size distribution of particles from a few nanometers to about 1 micrometer. So this was investigation of what happens to this radon attaching problem. But I thought then that the science of this was kind of exhausted. While it is an important problem, but scientifically I thought, well, we knew enough to do something. And I guess looking for something, one day I extended the probe of this instrument to outside. And then there was this, wow, what are these particles present in such quantities outside the window of my downtown lab at the University of Toronto? Huge concentrations, huge. I could guess that they are coming from traffic on the street, but still there was no literature on this at all. And then I thought, wow, this is really scientifically fascinating topic and extremely important. So this was the beginning of my journey with particles. Now, before I continue what happens then, I think I should tell you a little bit about these airborne particles, so you have the context of our, I wouldn't say discoveries, but our research and follow next. And I'm assuming that not everyone in the room is an expert in aerosol science. Airborne particles. Maybe a boring definition, what are the particles called aerosols? Aerosol is an assembly of liquid and solid particles suspended in a gaseous medium long enough to enable observation and measurement. So if I let this go, this wouldn't be an airborne particle because it would fall down immediately. So basically, the point is that generally we are talking about the two sizes up to about 100 micrometers, because anything larger than this is too heavy to stay in the air. So this is definition of aerosols, and in this image here, there's smoke. You will find lots of both liquid and solid particles, and they will be predominantly small particles. But then there are many other definitions. Dust and fog. Dust is often used like by people from outside the field, or lay people. It's used like anything in the air is dust. Not so according to our definitions. Dust is solid particles formed by crushing or other mechanical breakage of materials. And these particles are usually large, usually not smaller than 0.5 micrometers, like that on the picture above. On the other hand, fog or mist is liquid particles. So you immediately see that these definitions also point out to the sources, to the processes of formation, and to the sizes. Sizes. Size is very important. You don't see the particles in the air. Everything is small to our eye, so we don't have a perspective of the dimensions. But imagine that you were to compare these two objects, a sand grain and a boulder, piece of rock. Very different, a few orders of magnitude of difference. If you were to measure them, you wouldn't use the same instruments for a sand grain and a boulder, different things. But you may not realize that if you compare a petrol exhaust particle with dust, as I explained, the difference in size, orders of magnitude, is similar, which points to the fact that you cannot measure many of these particles using the same instruments. And then what the particles are, what the sources. So on the background of a human hair, about 100 micrometers, bacteria are among the largest, up to about 10 micrometers, raw dust about 5, coated dust about up to about 2, viruses are much smaller, up to about 0.4, and vehicle emissions are even smaller, up to about 0.2. Now, still with this classification and the purpose of the classification. Total suspended particles, smaller than 100 micrometers, particles smaller than 10 micrometers, PM10. We rarely use the wording of coarse particles, but fine particles smaller than PM2.5, and eventually ultrafine particles. Now, why it is important? I marked in red PM10 and PM2.5 because in every country there are now national standards to control them. And why it is important? I'll just mention this issue of fine particles, PM2.5. There was an amazing study published several years, a Chinese study on the role of PM2.5. So what you can see here, this was supposed to be a pointer, but it is closed it. Okay, I'm not going to try again with the pointer. On the left-hand side, you have pollutants in the air, starting with PM2.5 and different pollutants. And on the right-hand side, you have health outcome. Now, PM2.5, that broadband going to the health effects is by far the most important compared to other pollutants. So this is the role of particles on health. We'll come back to this again. But what was even amazing for me in that study was that the financial cost due to the impacts of this of the pollution, indoor air pollution, was amounted to 3.45% of the Chinese gross domestic product. This is a huge, huge amount. All right, but there's the world of these nano and ultrafine particles. Here there's an example of complexities between different fields of studies. If we look at the ISO definition, a nanoparticle is a particle with a nominal diameter smaller than about 100 nanometers. What is then an ultrafine particle? A particle size about 100 nanometers in diameter or less. And you are just looking at this and thinking, am I missing something here? Well, it's basically the same. However, the term nanoparticles is usually used in material science. Ultrafine particles is used in atmospheric sciences. So it also points out to the issue of terminology and the differences between disciplines. And on the top of this is particle shape. We can spend a lot of time on this, but we won't just showing how different shapes are. Petrol exhaust particles, asbestos, which is a fiber, and then the nanofibers. As you can see, none of this is round. There are very few particles which are round unless they are liquid. So this complex world of airborne particles, which we can look at from many different angles, PM10, PM2.5 for regulatory purposes, ultrafine particles, black carbon, secondary organic particles, metals, many of them are desert dust. Well, you can recognize these particles with pathogens inside, and microplastics, and many more if I could add the circles. I will talk just about 3 of these. Ultrafine particles, infectious respiratory particles, and a few words about microplastics. So now I'll continue the story, what happened after my discovery in Toronto. Very soon after, I got a position at the Queensland University Technology, where my journey with ultrafine particles started. So I established there this what's now called International Laboratory for Air Quality and Health. In 1993, 2 years after I took up my position there. Initially, it was called Environmental Aerosol Laboratory to stress the focus on particles, but particles in the air are not by themselves. So really it is air quality, and our focus always has been on health. Thrive now is an addition to this with a specific focus on building and building science. So now, and well, some years after we started this journey, we have answers to the question I asked in Toronto: what were those particles on the street of Toronto? So we now know, and this is not progressing. So we now know that most of the particles in the air are ultrafine, and that they are emitted directly by the sources, as I expected, transportation, aviation, road, and so on. So you can see here size distribution of particles emitted from compressed natural gas, diesel, petrol, and so on. So, but this is only one part of the story, and perhaps an easier part of the story. A more complex part of the story are the secondary organic aerosols, particles which are formed in the air. And I'll come back to this in a little bit later. This, you can see this red, we call it banana curves. This is the size of the particles with time. So they are formed very little, and then they grow, and then with time they are becoming bigger banana curves. So is this different between places in the world? There are big similarities. So that's one of the studies where we compared results from all the sites around the world. And on the diagram, you can see on the horizontal axis are sites, and on the vertical, these diagrams showing the sizes. So you can see these boxes. They are not big differences between certain groups of sites, but they are a bit bigger at the other sites. So urban background road site. I'm not going to go into details about this because it's just to show that there are no huge differences between certain classes around the world. What we also know now much better, what is the impact of these particles? Because if there were no impacts, if they were not doing anything, why would we worry about this? So, first of all, particle deposition in respiratory tract, exposure and dose. That's what happens. We inhale them, and they get into our respiratory tract. And we are talking about few areas of the respiratory tract. Now, remember the definition I gave a moment ago about total suspended particles. Now, we don't worry about them from the point of view of health. Why? Because we don't inhale them. They don't get down to the lung. But when we talk about particles PM smaller than 10 and 2.5, which is PM10, PM2.5 particles, this is where we have very well established epidemiology, WHO guidelines, and then national standards based on this. And then there's the world of ultrafine particles, which doesn't have any guidelines on standards yet. And these particles get to our body not only through respiratory tract, but also through olfactory, through the nose, and they get to where? To the brain. And that's potentially one of the biggest impacts. So for a long time, we had these curves, which is on the horizontal axis, mass median aerodynamic diameter, and then deposition fraction. So you can see that anything bigger than 10 micrometers is predominantly deposited in the nose, very little anywhere else. But if you look at what happens for particles in the ultrafine size range, they are predominantly deposited in the deeper parts of the respiratory tract. So this is the issue. We also know from many studies about exposure to these particles. In particular, that study, UPTEC, ultrafine particle from traffic emissions and children health, which we conducted in Brisbane some years ago, 25 schools across the Brisbane metropolitan area. The diagram on the left shows the variation in these particles with time. But the most important was inhaled surface area dose in the different microenvironments, commuting, home, sleeping, and so on. Now, you look at this and at these two circles. So this inhaled surface area dose is the lowest in commuting, the highest in sleeping. Is that what you would expect? No. But when we are talking about exposure, it's not just a concentration, but for how long are we exposed? And in traffic, those kids are exposed much less than home sleeping. So if you look at this from this point of view, surface a relative intensity, the situation is very different. So relative intensity is much higher. It's much higher in commuting, but much lower in home sleeping. So, so we understand this type of things now to understand the exposure concentrations multiplied by time in the sort of the most simplistic way. But we've also learned something else. The effects of exposure to these particles, still we are talking about the same kids. Ultrafine particles did not affect respiratory health outcomes in children, but caused systemic effects. Now, are you surprised that they didn't have respiratory impacts? The point is that they get very deeply into the lung and then they penetrate to the blood system, and that's where they have impacts, contrary to the larger particles which deposit in the respiratory tract. So this is the issue. We didn't study then penetration of the particles on the brain and what they do in the brain. So there've been our studies and other studies, but one really sticky point here is that issue of primary versus secondary particles. Some think that, well, primary is better, secondary is worst. Well, if you choose something in everyday life, but no, it's different. Primary particles are emitted directly from sources, like these black carbon particles by this track. But secondary particles are formed in the air from liquid, from molecular precursors, like this hydrated particle. So the issue here is that it's much easier to measure primary emissions than to figure out, measure, model, and so on, the formation and the presence of secondary particles and what happens to them. And they're usually liquid. Do they have the same effects? Well, we don't know. There was a study conducted a few years in Spain, in 3 cities in Spain: Barcelona, Huelva, and Tenerife, Santa Cruz de Tenerife. So what they set to do is to conclude the impact of primary versus secondary particles. And what they did is they looked at the total and then primary, which are related to black carbon, and secondary low in black carbon. So that's what they measured. Did they have different impacts? What they found out was that mean concentrations, all 3 cities were similar, slightly higher black carbon concentration in Barcelona and Tenerife. However, association with daily mortality in Barcelona and Tenerife with N1, which is primary, in Huelva with N2, which is secondary. So, what's the answer? And there were very few studies like this. We don't have the answer. And the biggest issue in all of this is that to this day, we don't have exposure-response relationships to ultrafine particles. And until we have this, we cannot have health guidelines or standards. Now, what is exposure-response relationship? This is an example of exposure-response relationship to PM2.5. So that's acute lower respiratory infection, and you can see increase in concentration and the impact, and you see how that relationship is shown. The one on the right is the study based on 41 different cohort studies, and this was commissioned by the WHO when developing the guidelines. So you can see exposure response curve. Based on this, you can say these concentrations, that's where you expect the impact. But nothing like this exists for ultrafine particles. And that situation stayed like this for decades. This is a quote from the WHO Air Quality Guidelines 2005. This was only mentioned on ultrafine particles. While there's a considerable toxicological evidence of potential detrimental effects of ultrafine particles on human health, the existing body of epidemiological evidence is insufficient to conclude on exposure-response relationship ultrafine particles. I was part of this activity, and this was the only quote I kind of helped to smuggle to that document as a mention of ultrafine particles. Well, we studied the particles, we colleagues in Brisbane, in Australia, around the world, and the situation continued. And then there was a conference that was 2017 in Casino, and we started discussing this, and in that frustration, we know so much, and we can't use this knowledge, what to do? So we set as a group, and we developed this white paper for decision makers about ultrafine particles, saying what they are, what we know, and what to do. So we were then very pleased that this work found its way to the current WHO air quality guidelines as a chapter, ultrafine particles good practice. So now we have a whole section in the guidelines, and I was even more delighted to see when at the end of 2024, this work was acknowledged by the EU directive and recommending actions on ultrafine particles measurements. So this was a huge progress. Well, it is still, of course, not possible to set guidelines, but what was possible to include in the document the so-called typical values based on literature review. So this typical 24 hours values in clean environments below 10 to the third particles per cubic centimeter, urban background below 10 to the fourth, and likewise hourly below 2 by 10 to the fourth. Well, it stepped forward. So this can help to distinguish between low and high particle guidelines and guide controls. But there was also a recommendation there for action. And that recommendation for action is effort should intensify to utilize emerging science and technology. Models, tools to do something about this. And in particular, to resolve that issue of primary versus secondary. Okay, that's great, but the complexity of these instruments hasn't decreased over the years. So it is still basically impossible to do this. Because how to scale it? If these instruments are big and bulky, have lots of problems, required experts to operate them, not feasible for large deployments. So, well, scientific research continues, but larger scale epidemiological studies haven't been possible. However, using emerging science and technology, there's an instrument which is about this size, Partector 2. It's based on devices, its predecessor, but this one is introduced quite recently, a few years ago, is based on unipolar diffusion charging and has 8 size channels from 10 to 300 nanometers. And we saw that it performed well in several studies. Can it be used for epidemiological studies? Initially, some say no. Why no? Why not? Why not? Because those big instruments, they measure in about over 160 channels. We have very detailed distribution to point to this primary, secondary. This is only 8 channels. But that 8 channels, we argued, it is enough. Using these measurements and some modeling and machine learning, we can do this. So our aim was, we set an aim about a year ago, 2 years ago, to conduct a study for 1 year to show that the outcomes of measurements are similar to this complex instrument and that it is robust, that we can use it, it doesn't break down, doesn't lead to lots of data. And we did it. We did it. So colleagues from 18 sites bought this instrument, which is about 12,000 euros, on their own expenses, placed there, and it operated for 12 months at each site. So that's one example from Birmingham. So you have here the results from Partector and from SMP, Scale Mobility Particle Sizer. How does it compare? Very good. Of course, there are some differences. And of course, I showed the best example. Why wouldn't I? But still, based on what we see, we can vary. Now it's a direct pathway to use this for epidemiological studies. So that's the direction, and with particular focus on brain health, and what we hope that this will lead to future WHO guidelines and in terms of control, concentrations, and exposure. So that's where we are. This is kind of a, I don't know, happy story which lasted 3 decades so far, but it's progressing in the scale of timelines of humanity. 3 decades, there's nothing. But now it's a different issue, very different issue. Infectious respiratory particles. Particles which you and I emit all the time. My story, or our story, started actually with what happened in Hong Kong, which I don't know whether all of you here present remember this, but I'm sure you've heard if you were not part of this. So this spread of SARS-1 in Amoy Gardens in 2003, it was big mystery what happened there. How come 300 people were infected from one person who spent 1 night there? And lots of investigations, and particularly Hugo Lee was very highly involved in this. There was a group of epidemiologists established by the WHO, and they couldn't explain what happened. So WHO was trying to set up another group, aerosol experts, to help resolve the mystery. I was invited. I was petrified about the idea of coming to Hong Kong at that time. And it didn't happen because by that stage there was no evidence on the ground. But then I again started looking through literature. And what I found over the span of 60 years, 3 papers published on the physics of these particles. I thought, wow, such an important topic and so little has been known. So what we did, we applied for funding from the Australian Research Council. We got the funding. We built this tunnel. This is Professor Chris Chow's student, Pam, sitting here. You remember all of this, the discussions about how to build. My visit here when we were sitting, visiting your lab and sitting, doing it in a tunnel, do it in the chamber, what we do. We decided on this. I'm not going to go into details about this, but this was the sort of most controlled way we could do it. And through many publications and studies, continued study over the many years, we showed what is the size distribution of particles from human respiratory activities, what affects it, and so on. Well, we then talked about how to use this for infection control. So that was my first paper on this topic, but I was not the only. I'm sure you remember this paper. And we were already pointing out to what to do with this. Well, ventilation. We need to get them out of the air. So that was what we were pointing. So when this pandemic came, the mechanisms of airborne transmission were very well known. But when we saw this tweet by the WHO Director General that the virus is not in the air, well, this was pure nonsense, right? So we started a battle which took about 3 months, from at the end of March 2020 to July 6. Why did the battle finish there? Because after huge efforts, we managed to publish this open letter to that open letter, as we called it, to the WHO and national public health authorities. It is time to address airborne transmission. How and why? So this was this group 36, which Professor Chen mentioned, and the scientists which supported it. The next day after this was published, the WHO acknowledged evidence emerging of the airborne spread of the novel virus. Evidence emerging. We didn't do any studies this. We knew that. So this is the infectious respiratory particles we studied for the past 2 decades. But all right, this was the moment when the wheel started turning the other day. Slowly, but it started. This was then considered by sort of many, the Washington Post, one of the 4 key elements in fighting the pandemic. And the way forward. Well, they will start turning. Then there were sort of attempts to say, well, all right, that happened, but it was all due to terminology. We scientists call everything aerosols. Medical doctors call droplets what is larger, aerosols smaller. It was all terminology, which of course it wasn't. Terminology differed, but physics not. So some years later, in 2024, after about a year and a half of work, WHO published this document on the terminology. So potential modes of transmission of infectious respiratory particles. Now, I'm using now only this term, infectious respiratory particles. I never use droplets again, not to mix it with the old terminology, because that's what I suggest use. Particles. Particles is right from from science and from medical angle. So this is the term used. Then there is sort of more detailed explanation of the different modes. And we're not going to go in detail of this, but the most important here is that this is the airborne transmission is stressed here. So we could say we finally won the battle of accepting science of airborne transmission. Have we? Kind of, but we still see situations when it's going back to the old bad habits. So when this outbreak happened of hantavirus, WHO was still kind of pointing to other things which were not really airborne transmission. So we had to fight against, it's not fight this time, but still bad habits don't stop from one day to another, from 1 year to another. It takes time. So we are on the trajectory, but we are not fully yet. But now, going back to the issue of particles. Can we detect infectious respiratory particles in real time and the pathogens they carry? We can detect particles in real time. We can measure PM2.5, we can measure particle number, we can measure other pollutants, CO2, which is measured in my handbag there. But ideally, we would like to measure in real-time pathogens. It would tell us that there is that SARS-CoV-2 floating or influenza virus floating. Can we do it? This is what would be involved in real-time detection of airborne pathogens. So it is the person exhaling, infected, the person being warned, and then the elements which would be part of this, components of real-time airborne pathogen detection, the sampler, the assay, and so on. What do we mean by real-time? Is 1 second, 1 minute, 1 day? We concluded that we are talking about the detected and reported within less than 1 hour, because it helps protection. Now, but I hope that you can see the title of this paper, which was accepted very at the beginning of August by Henry Oswin, our postdoc in Brisbane, now back in Bristol. The real-time detection of airborne pathogens, science fiction or imminent reality? Science fiction or imminent reality? Well, what we analyzed in this paper are the key challenges with this real-time detection. First of all, sensitivity, which is capability of detecting airborne pathogens. The issue is that the concentrations, considering the dilution and so, are usually at the detection limit. Like, for example, if you look at the amount of emitted SARS-CoV-2, it's 0.5 genomes per second. It's very little. So we have very, very low concentrations. That's one. Specificity. Different components of the detection system must be developed for each different pathogen. So this is a problem. If you remember, it took almost a year before the first lateral antigen test for SARS-CoV-2 was made available to the public. A virus change all the time, mutate. So following this, it is a challenge. And then scalability. If we want this to be low cost, such that we could have it in every room, like this little monitor I have in my handbag, that's not possible. So basically, it will happen. It will be possible. There are massive, massive amounts of money invested into this. It will happen, and it will have applications in some specific environments, but it is a science fiction that will have it in every room anytime soon. But luckily, in this situation, imagine that what I emit is pink. So it's pink. In that pink, these are these green beads. These are pathogens. So we are saying that we won't be able to detect them in real time anytime soon at scale. However, there's also something else. That's CO2 emitted all the time. And we can measure the CO2 very, very easily. I'll eventually reach to my handbag to get this, but I'm sure the others. So this is this size. We can measure it very easily and use it as a proxy for these pathogens, for the proxy for infection transmission. As a proxy, it's not sort of perfect, but it's good enough. And then we can use it for adjusting ventilation accordingly to make sure that we get them out of the system, or we filter, we do something, that direct ventilation, so-called event ventilation. And then we can use it for regulation. So to make sure that we have standards for indoor air. So you can see that in this situation, in the situation of infectious respiratory particles, it's a very different control strategy to what we are proposing now for ultrafine particles. Now, and the last short story is about microplastics. I really remember my visit to Solomon Islands in 2019, this idyllic beach, and no one around, completely deserted, no houses around, and all this is covered with this plastic rubbish. I asked my colleagues where it's coming from. They thought that some may be coming from Honiara, from the capital, because the rubbish collection is not that good. But they also said that it's coming from the currents from the ocean. To me, this was really horrible to see something like this. But the reality is that the plastic production over time, since its discovery in 1907, has been increasing and increasing, reaching unprecedented levels, and this continues. This is the plastic production and plastic usage. Well, we can say recycle it, but the reality is that only very small fraction can be recycled. So really, we need to reduce the plastic use. This is the direction. Now, the complexity of this is immense. And well, last year, almost exactly last year, negotiations on binding global treaty to do this collapsed, basically. Why? This was explained in this paper. The issue is that fossil fuel producing nations vetoed measures including capping plastic production. So what's going to happen in the future? It will keep growing like this. WHO produced a report. I was part of this a few years ago, pointing to quite a number of issues, starting with understanding what they do and terminology. So not leaving the whole wording, but microplastics, according to this terminology, is from 1 nanometer to 5 millimeter. Millimeter is not micro. So that's really a problem in this. Nano is up to 1,000 nanometers. So you can see the whole confusion existing. And then recommendations selected. And again, I just highlighted the main issues, not to go through all of this, is the substantial limitations of the available information. We know very little about these particles. Standard methods don't basically exist to measure them. Of interest are particularly those smaller than 10 micrometers, because we can inhale them, but understanding is very limited. So isn't this phenomenal that something like this, which is growing exponentially, which is everywhere, and we know very little about this. Now, size of particles matters, and that's what we did a year ago with colleagues. We've reviewed what's known in a sort of more science-oriented way than what the WHO report is. Physical fragmentation of plastics into airborne microplastics. So like this vehicle on the road. So what do we know in a quantitative way? And conclusion is really grim. So overall, a very complex picture regarding characterization of microplastics in the air. And most studies reported fragmentation processes and that something is generated. But however, most were laboratory studies which has nothing to do with real environment. So that was the conclusion. Most field studies do not report concentrations, so it's more qualitative. So basically, the current state of knowledge is very limited. Isn't this really? It is extremely complex because while they are everywhere, measurement methods which we use for measuring total particle concentration, size distribution, and so on, we cannot distinguish which of them are microplastics. We have no time to talk about things like this. But something amazing which I found, and I thought, wow, this is a report recommendation by the US EPA about historic actions to protect Americans from microplastics. Now, it's a small print, what it recommends inclusion of microplastics as a priority contaminant. Is it good? You don't know where it's going, and you don't know whether to say yes or no. Yes, it is good. But what it is the proposed? Elimination of microplastics from the human body. How will you get microplastics from human body? So rather than reducing the production and the use of microplastics, remove them from human body once they are let there. I think this is a completely misguided direction. Well, in summary, to close. How to control the world of the particles we inhale. It is a very complex world from a scientific point of view. And I hope I managed to convey the complexity, giving these three examples of the three types of particles. So we need to first scientifically understand it. But airborne particles are part of a complex building, person, environment system. So we also need to understand all the interactions. What does it do? Controlling the system means controlling source emissions. If we can, then all that microplastics, concentrations, when we are talking about particles from human respiratory activities, and human exposure. However, little of this will happen without regulatory oversight. Without regulations, it's very difficult to expect something happening voluntarily. This oversight must be based on science due to the complexity of the matter, and different measures, regulatory measures, must be taken dependently on the different types of particles, what's happening to them, and how to control them. And that's where our role as scientists is, from many different different areas, contributing to this interdisciplinary science. Build the science, but then talk to the decision makers what to do about them. Thank you very much. 谢谢.
Thank you, Lydia, for very inspiring talk. Yeah, you not only present the past work, but also pinpoint to the future direction of research. That's great. Now we do have the time for discussion.
Professor MORAWSKA, it's a long-standing issue for striking a good balance between sensitivity and specificity in detecting bioaerosols or pathogens or airborne pathogens. Say, like using the traditional, say, LAM, digital PCR, so and so forth, for considering the cost, operational ease, and versus the other arm for, say, using sequencing or mass spec for the mass. So would you mind sharing more how do you achieve, because you mentioned that there will be a paper going to publish, how do you strike such a balance in doing that?
This paper has been already published. That's about the particles imminent reality, science fiction of imminent reality. So that paper is already published, is in press, but the link is already available. It is not really setting a balance between them, but what we were trying to point out in the paper, that if we put enough resources, if we put enough effort, we can achieve that situation that in this room, having all this set up, we would be able to detect the specific pathogens. But the fact that we can have a whole laboratory here in this room and protect people potentially in this room, it doesn't mean that we can use this kind of facility and effort in every room, even at this building across the world. So basically the idea is, what can we do? How can we achieve a simple, scalable solution such that we can protect people? And what we say that it is not through these very complex detection systems, which are useful, important, we need to do it. But if we want to protect people everywhere, we need to ventilation, And we can use CO2 as a proxy for infection transmission for these pathogens to tell us immediately, is the ventilation adequate or not, increase ventilation or put ventilation and so on. So this is the balance. Hugo, can you please get from my handbag this black handbag? This is actually the monitor. I hope it is there. No, in the black bag, not in the just black bag. Yeah. Hope I put it here. It or I did. No, I did. So I was changing this, but basically that CO2 monitor is this size. Is this size, and it costs dependently whether you what you want to get it in communication. So it's $200, even less. So you can have it in every room, but you cannot have this lab in every room. So this is the balance. That was the issue. Actually, you had Professor Chan. We had a very interesting conversation before this lecture about saving lives.
Yes.
Saving lives. So, what the story was when we convinced the world that it's airborne, how the virus airborne, how many lives we've sent. So we are saving lives this way. But your comment about how you save life, how we save lives doing this measurements, ventilation, that was actually quite amazing. I think it'd be worth mentioning this to the answer to this question.
Yeah, we actually before the lecture we discussed about how the COVID-19 virus is transmitted in the cruise ships, and you can quarantine off the shore or on shore, and off the shore because the ship is very small, and then it's very easy for virus to transmit from one room to another and cause a lot of death. But if you quarantine on shore, the space is big, then you don't get many people infected that can save a life. That was the discussion.
Right, and then they listened to this. In the US, they listened to this, and that demonstrated there were significantly fewer cases and significantly fewer deaths when they listened to this. So as I said, it's through this direction what we pragmatically can do, and not necessarily through most complex measures, which are impossible to use in every situation.
Yeah, I can also supplement the work done by Professor Lee's group and also his students on a restaurant during the pandemic, which show the airborne particles really cause the infections of other diners in the same restaurant. Any other questions? Okay, Professor Wang.
Hi, Lydia. Thanks for the nice talk. So my question is about control of ultrafine particles. So right now, as you know, we have standard for PM 2.5, and there has been long discussions about for controlling, for the argument to the need to control ultrafine particles too. But in your experience, what was the obstacle or hurdles in pushing for control of the ultrafine particles?
The single most important obstacle is that we don't have exposure-response relationships. That's what I was trying to. Without this numerical relationship, governments are at loss at what concentration level, what to do. And there's no solution to this. That's why we are saying it is extremely important that we have exposure-response relationships. And that's how it started with controlling of larger particles, PM 2.5. Like now, countries look at the new WHO guidelines for PM 2.5, and they are discussing how to lower the national standards accordingly to this. So once we have health guidelines, which are based on exposure response, we can move to control. Without this, it's just, okay, I like this value, I think this value is good, and we'll never agree, or no one ever agree.
Well, there are some questions from the internet viewers. One of the question is, there are so many different type of particles indoors. Which one is the emerging sources, and then how to control it?
This is a very good question. This word emerging particles, when we try to attract attention to what we do, or when we apply for grants, we say this is an emerging pollutant. So I still hear this about ultrafine particles. This is an emerging pollutant. How long we have it? It's not emerging. The same we hear about microplastics. It's an emerging pollutant. Since 1907, when production started. So it's not really, we don't have really emerging pollutants. They could be specific chemicals, part of the particles, but in terms of general classes of pollutants, we know what the pollutants are. Now, ideally, in the ideal world, we would like to somehow instantaneously scan the concentration of everything in this room. We would find out that there are at least several thousands of everything, if not more. And we would like to automatically say, okay, this is a problem, and then do something. Is this realistic, or this is science fiction? It is science fiction. There's no way in the world that we would be able to, in any time soon, do instantaneous measurements of all the pollutants in all the places to control them. But pragmatically, if we know that the pollutants they come either from the sources here in this room or in this building, or they come from outside. If they come from here, we should get them out. We should, in the first instance, we can control them if we can, or we should get them out. We can't control people. That's a different conversation. We can't control emissions. But we must get out what's generated here. On the other hand, if the pollutant is coming from outside, we must prevent it. So even if we don't measure every pollutant coming in, generate, and so on, but just controlling PM2.5 particles which is mass concentration, that's how it is, just controlling this, if we detect the concentration here is high, but we need to have a second monitor, a sensor outside. If here is high, outside is lower, what do? We increase ventilation, or we look what it is the source. And then if we lower the concentration of PM2.5 here because of the sources here, we also lower the concentration of anything else which is emitted from the sources. On the other hand, if our monitor would say outside is higher than here, and we stop the stuff coming in, so not only PM2.5, but also ultrafine particles, also other pollutants are prevented as well. So we cannot and will not be able in any time soon able to measure and control every single pollutant. We should try to do everything possible to lower source emissions, and there's another conversation, particularly in terms of industry coming up with all kinds of sources. But otherwise, we should use pragmatic methods we have now, and this will reduce concentration of most of the pollutant.
Okay, let's another question. Yeah, okay.
Hi, Professor. I think your answer is very impressive, but I have a question. I mean, maybe on the surface, all the answer is different because it's point-to-point solution, right? Just as you mentioned before, under a different situation, we may have to adopt a different methodology or solution toward it. So it's very hard to make it make some effect to the policy. But what if we focus on the hidden propagation? I mean, if we focus on the point-to-point answer, the answer will be different. But if we focus on the hidden logic to the transmission logic. Maybe it's common, and you will find the common logic in different, maybe just certain types of different types of the propagation things. So it means that women can get the outcome which comes from a group of answer collection, and under different situation, women can just pick up one of the answer collection. So it means that if when we want to make it down to the earth, when we want to pick up some solutions to the policy, we may not have to put every answer to be the same. We just need to obey the hidden logic of the propagation. And it can also build a great achievement to the solution. Is there any possibility to resolve these things? Furthermore, if we can obey this kind of rule, it means that maybe the trajectory can be more predictable. Because if we focus on the point-to-point solution, each answer, each experiment is just to be used for targeted the certain situation. It means that maybe the trajectory will be deviate to the future. So I wonder if we transfer our logic to the hidden logic of the propagation. Is there any possibility to focus to solve to this problem? Thank you.
If I understand correctly, what you are saying is that can we have kind of something, a big picture guidance, what to do, rather than point-by-point solutions? So the big picture is what we are, from the big picture, we have standards for outdoor air. We have standards, and this standard say that concentration of this pollutants, whatever, 6 point whatever, must be below this level. But in this standard, this high-level standard, we don't say exactly what must be done. This is the next level. And that next level then is investigation what to do in this situation. In the situation, let's say, of this town, when the main source of pollution, let's say it's a factory, well, you need to do something about this factory. On the other hand, if you are talking about a different town, if the main source is congestion and vehicles, you need to do something about this. But this is where we are going down to specific solutions. But the overall aim is the reduction of pollutants below this level. And the same, we are talking about indoor air, for which no country yet has mandated standards. So we are saying that the 3 pollutants, which can already be measured in every space, which is PM2.5, CO2, and CO, if this is measured, keep these pollutants below the level suggested. So doing this will require different actions in different buildings. If we are in a naturally ventilated school, you'll do different things than if you are in a building like this. But if we agree to this overall, then different things will follow. It is in a way, if you bring the comparison to medical diagnosis. Let's say a medical doctor, and something where I'm also stressing is that to do something requires experts. It may appear to some that, oh, well, I learned something about air quality. How am I going to control air quality in this role? No, you cannot. We cannot expect from non-experts because it's complex. The same way, we don't expect non-experts to heal us. Our medical doctors have to be trained. So let's say diagnostic, if a medical doctor, after the test, detects that the blood level of a patient is above something. So we have this oral. Blood level should be, to be safe, should be below whatever it is. Right? So it is not yet a solution what to do. Medical doctor then looks at the person, looks at the situation in general, and based on this, then administer the course of healing. That's how it is. But we have medical knowledge which established that the blood level or whatever it is should be below this. So I'm not sure whether this answered your question, whether that's how you saw it.
Yeah, it's probably answered. I can still see the bottleneck of the future science. Okay, thank you.
Yeah,
Thanks, Lydia, very much for a very insightful talk, and I'm very interested in what you're saying about the particle and brain health. Okay, so compared to very well established respiratory deposition of particles, right? So how well do we know the particles move all the way from nose to olfactory bulb into the brain? How can we model that physical process? How well have we achieved in this area?
Well, when I show this diagram of the deposition of particles dependent on size in different parts of the respiratory tract, so we have curves for this, for smaller particles, for bigger particles, and that research has been done. And interestingly enough, this curves exist. Even so, we cannot directly measure deposition directly in this. So it's done. But curves like this don't exist for the brain yet, because studies like this simply haven't been done. So there have been publications pointing out to the role of olfactory penetration to the brain, but nowhere near enough that we could come up even with curves for this. So this is our objective. But to do this, you need to have sufficiently large study. If you have a few people, well, you find out something, but still it won't be enough to achieve general. So we need to have a sufficiently large study, which is an epidemiological study, which goes back to the issue that we must have robust methods of measuring this. So this is our sort of full focus right now. Epidemiological study to tell us what's happening with the epidemiological, but also mechanistic. How does it happen?
Thanks.
If anyone wants to join this, very welcome.
I'm interested in.
You are in. There's one person.
Yeah. Hi, Professor. First of all, thanks for the inspiring sharing. And actually, I'm a student from the School of Design, and I still find today's presentation informative and give us a brand new perspective to observe the micro world. I mean, if you don't mind, I would like to ask some questions about the balance between the visual or the data contributing to our practical research, because I could see the contents shared while your inspiring presentation. I can see most of the contents is driven by data, right? It is quite critical. And I'm just wondering, beyond the data-driven part, could some part or elements included in the research could be also defined as the visual-driven? If yes, I will appreciate you can share more details about the application of the visual-driven elements that could be contributed to your research, and how you are utilizing the visuals to solve the problems in the practical research. Yeah,
So
thank
what
you.
did you say, data-driven or vision?
Visual, I mean, the stuff we can see it while our eyes or
Vision. Well, I guess in a discovery, in the course of action, we use all the tools we have. If we just look, if I understand correctly, because I'm not sure whether, if we look at things, we cannot quantify things. So vision, like looking with my eyes, I can't see the particles, I can't do anything, if that's what you mean, the vision.
I mean, the visions here could be also defined as the contents that we can observe while some specific equipment contributing to the research. That could be also one of the other kinds of the vision, yes.
Listen, there's absolutely no only one tool we use for research, because whichever tool you use, it gives you insight from that particular perspective. And sometimes it's because you have lots of data and you say, wow, that's interesting. But on the other hand, you don't have data, but you get an insight, okay, I can see what occurred here in this chamber. Or you can come up with an idea, okay, I saw these people being sick. what contributed to this? Or I have an idea. At the end, we need to understand mechanisms. So you look at this and you develop an idea. That's why I thought vision. An idea vision. What is driving this? And then to explain what is driving this, what's the mechanism behind this, you use any possible tools you use. So there's no one single tool you use. It all depends on the aim. And I often stress this, that dependently of what is the aim of your investigation, you use very different tools or very different set of tools. But the first, you need to identify what is the aim. And sometimes just exploration. Okay, I'm just curious what's here. But sometimes it's, okay, I know that there's a problem here. How am I going to solve it? But if to know the solving, I need to know to quantify the problem. Or, as I said, it is what is the aim, then you use the tools, and sky's the limit what tools you use.
Okay, thank you.
Well,
Yeah, I'd like to take the opportunity to ask you a question. You mentioned about this microplastic at the end of your lecture. You know, in the drinking water, I can imagine there's a lot of microplastics, but I don't know how much in the air. If you compare what we inhale every day, because we drink a lot of water, we also inhale a lot of air. So which one is more important?
I wish I had an answer to this, but the complexity of these measurements, like through the WHO report, from our review of literature, there are no answers. And the problem is this, that measurement of what's in the air in terms of microplastics is extremely complex, because microplastics are not the only particles in the air. And actually, in terms of number or mass, they constitute a very small fraction. So you cannot, based on any simple measurements, be it mass size distribution, number size distribution, you cannot conclude on the content and fraction of microplastics. Likewise, you cannot conclude on the content of pathogens, because the number of pathogens in the air in terms of mass number is significantly smaller than anything else. So you cannot use any simple measurements to say, okay, there's more microplastics here than this. You need to conduct very specific studies, collect these particles. Usually at the end, you look at the electron microscopy and so on. It's very detailed side. That's why we have so little studies that we can't really properly answer this question. There was the recent conference in Glasgow in May, where the experts in inhalation from sort of medical perspective reviewed this, and they the instrumentation they do. The picture is very grim. I think Ugoli has a solution.
Okay, maybe the last question for you. Do you want to ask? Can you turn on the mic?
The leader has given a great talk. Big title, Current Problems of Science. And apart from, we do not know many things. Hence, the regulation is not possible at this moment. But regulation is also important. I think you have done great work in your life helping us. So one leader is not enough. We need more leaders. And in terms of regulation and current problem science, there's a distrust of science in the world. And this is where, how did you overcome? And we can continue to work on this. This may be more important at this moment, although with AI. And I guess that's another side of the current problem science. And how did you, you have done so much.
Well, two questions. We don't know everything. So how to regulate? But I often say, and I have some slides in other presentations, we don't know everything, but we know enough to act. We know enough to act if we act wisely. We have that paper published with Professor Tunga Salthammer from the lessons from a COVID pandemic in relation to ventilation. So if we act based on these lessons pragmatically, we can go well above what we don't know. We'll never know everything, but we know enough to act. So there's no doubt that this is possible. Now, this aspect of how to influence action, which is then interaction with the decision makers, this is an extremely complex problem, and it differs between countries. Every country has different regulatory system. Given now the situation of indoor air quality standards, which we are trying to influence, that they are mandated in different countries. I'm working closely in Australia about this and have done a little bit of work in Poland. And I already see that we completely different regulatory trajectories in these two countries. In Australia, this will go, and hopefully it's going. I can't say anymore, but I hope I will eventually, and not in too distant future. It is going through work health and safety, because Australia has such a strong framework for workplace health and safety that any risk, any harm potential must be taken control. So this is there, and we are talking about mandating indoor air quality standards in public buildings. And well, public buildings is everything which is not our residence. So there are lots and lots of places. So this is the direction in Australia. In Poland, on the other hand, they seem to focus and they want to start with schools, demonstrating through schools. What will be the trajectory in China? I don't know. But considering how effective Chinese regulations were when outdoor air quality standards were introduced in 2013, and the concentrations of pollutant went down and are going down like this. So this was based on science, on the knowledge and actions, and then the enforcement. So again, it would require to consider which directions, through which government regulatory process it goes. So first is identifying which way it should go, and then trying to talk to those people. That's probably, and to use a lot of patience.
Okay, well, I definitely know there are more questions, and especially those from the internet, but unfortunately, we don't have enough time, so we have to conclude the Q&A session here. And Per, I would like to present you a small souvenir. So this is souvenir is with your name and the title of a lecture today. I'd like to invite Professor Lee and Professor Guo to the podium. Okay. Thank you very much. Yeah, let's give Professor MORAWSKA another round of applause. And I would also like to thank all the people here and online for attending this lecture. So please keep tuning on our announcement for the next lecture. So this lecture is adjourned. Thank you very much.